have the next topic, which is the moment of inertia. So moment of inertia, it identifies the resistance of the materials to the flexure or bend. So we have here the parallel and perpendicular axis method. So for the parallel axis method, we have IL, or the inertia, is equal to the integral of the lambda squared dA, where dA is taken parallel to the axis L, and then lambda is the distance of dA from L. So this is simply the distance of the dA, or the strip, that we'll be getting to the axis of revolution. So for the perpendicular axis method, that is will be just base, height, cube all over. If you are we are if you encounter any polar moment of inertia, so we'll be using the polar coordinates here. So J is equal to the integral of r squared dA. So you'll get here by Pythagorean theorem, of course, r squared is equal to x squared plus y squared, multiply dA by both sides, you'll have this, and then you'll have this if you get the integral of both sides. Okay, and then you'll have just J is equal to Iy plus I. So for the area of bipolar curve, the R must be a function of theta. And then your J will be, there's a shortcut here, which is J is equal to the 1/4 integral of R raised to 4d theta. Okay, so for you to be able to appreciate more the formulas, let's get into the first example. For the first example, we have find the moment of inertia of the area bounded by the curves. So y equal to x cubed, y equal to x cubed, and then y equal to 8, and then x equal to 0. With respect to, so we have 3, which is the first one is y-axis. Okay, so this is already the graph. So we have here, this is y equal to 8, right? And then this one will be your y equal to x cubed. Okay, and then x equal to 0. Of course, this will be your x equal to 0. Okay, so you have bounded by the curve with respect to the y-axis. Of course, if this is the y-axis, so this is the first one. Okay, so for this is for letter A. Okay, for letter A. Therefore, we have to take, if we will use the parallel axis method, so we have to take the dA parallel. Parallel. So if that is the axis of revolution is at y, so this is the strip that will be get. Okay. Mhm. So that is the strip that we will be um, considering, right? So as you can see, that strip is they have a clearance here, of course. So what will happen here is if we have to subtract the two y's. Okay, so this is a y. So this strip method is, of course, the lower part will be your dx, and then this upper part will be, of course, the upper part will be your y2, and then the lower part will be your y1, which is this is the lower part. Okay, so y2 is the upper part because this is the upper, and then this will be your lower. So what will happen here is your dA now with that, your dA now will be y2 minus y1 dx. And then your lambda, okay, your lambda here is the distance of the axis of revolution to the dA, of course. So this will also, it will be this one, which is just x. Therefore, your lambda here is that. Okay, so using the parallel axis method, you'll have um, let's say Iy, right? Iy is equal to the integral of lambda squared. Okay, so lambda squared dA, right? So this will become lambda is x. So x squared, and then your dA will be y2 minus y1. Okay, y2 minus y1 dx. Okay, and then equal to integral of x squared, and then we have to get the y2 and y1. So we already have y2, which is 8. Which is, actually, I think this should be y1. Okay? So this should be y1 and this is y2. Okay? So y2 will be x cubed minus 8 okay, dx. But we still have to get the intersection. So if you will just make here y is equal to y, therefore 8 is just equal to x cubed, therefore x is equal to plus or minus, right? Plus or minus. Therefore, you will be getting the positive 1, of course, and then that is from 0 to 2. So this is 0, 0 to 2. So that will be your I, y. So if you will just enter this in your calc, you will have here IY is just equal to 10.3. Then this will be your answer. If with respect to I, to Y. So let's get into letter B. So it will be just the same, right? It will be just the same. But the difference here is we have to get, instead of the strip being vertical, we have to get it horizontal because now the axis of revolution it will be revolved with respect to the x-axis. Therefore, your strip now will be this one. So therefore, for that one, you'll have dy, right? And then this is just x. That will be. And then the distance from the x-axis to the dA is just y, right? So therefore, we can say here that your dA here will just be x dy, and then your lambda here will be y. Okay. So using still we are still using the the parallel axis method. Okay. And then next we have to get the values of the intersections, right? So the values of intersection is that will be with respect to y. So the lower part is the origin, of course, that is 0, and then the upper part will be 8. That is y is equal to 8. Therefore, okay, this line is y equal to, right? Y equal to 8. Now, getting now ix equal to the integral of lambda, which is y squared, and then dA is equal to x dy. So what will be the value of x? What will be the value of x? Okay. So we'll be getting this one. So y is equal to x. So getting that y is equal to x cubed, therefore we can say that x is equal to y raised to 1/3. Okay. So integral of that is 0 to 8, right? And then y squared x is y raised to 1/3 dy. So if you will get this answer or input that in your calculus, you will get an answer of 307. Okay. Okay, so we have the letter C, which is now we have to rotate it at the line y equal to 8. So I already drew it again. As you can see, this will be y equal to 8, and then this one will be y equal to okay. And then but now the revolution is here. Okay, revolution is here. So getting the parallel axis method again. So the parallel axis method is still this one. So we can still use the horizontal strip, right? Horizontal strip. So this will still be um, dy, and then this will be x. But the problem is the lambda. So the lambda, as you can see, this is y equal to 8. Therefore, this whole is 8, right? And then we can say that this part is y. Okay? Therefore, this part we can say that this is just 8 minus y, and that will be your lambda. Therefore, your dA here will be um x dy, and then your lambda here is 8 minus y. So if we will now get the I at y equal to 8, the inertia at y is equal to 8, the integral of the lambda, which is 8 minus y squared times x dy. X, okay? And then what will be now the limit? The limit is still the same, it's still 0. And then integral of 0 to 8, which is 8 minus y squared, and then your x now will be, you still get the same x, which is y equal to y raised to 1/3 dy. And then if you input this in your calcu, you will get an answer of 197. So let's move on to the next number. Okay, so we have the second example. So we have find the moment of inertia of the solid generated by revolving the area bounded by xy equal to 4 and x equal to 1, x equal to 4, and then y equal to 0. About the x-axis with respect to the x-axis. Okay, so what you will do here is already draw the graph. The xy equal to 4, that is actually a special case of hyperbola, which is a rectangular hyperbola. So the red line, the red font, or the this one, that will be your hyperbola. Okay. So obviously there will be another pair of that on the other side, which is on the third quadrant. But I won't be showing that anymore since we only need this part. And then we have to get the x equal to 1. Let's say that x equal to 1 is here, and then x is equal to 4 is here. Okay. Okay. So this will be x equal to 4, and then this one will be your x equal to 1. And then this curve is your xy equal to, and then y is equal to 0. That is obviously just the x-axis. Okay. So this is your y equal to 0. Okay, so getting the inertia of this one, we can use another formula. Okay? So another formula is IL is equal to 1 half mr squared. Okay, let me just write it again. Okay. So that is 1 half mr squared. So what are those? Your m here is usually your dv. Okay, so you can get dv just a volume. So you can use this method, cylindrical shell, or the washer method. Okay? Either. So in this case, we'll be using this method. Okay, so this method, which is the first one and the easiest one, this method. And then your r here will be, so you can see you have to get the axis of revolution here will be at the x-axis. Remember that if you're using this method or this formula, the axis or the strip that you will be getting must be perpendicular to the axis of revolution. So this must be vertical. Okay. Okay. So this will be your y, and then this is the x. Okay. Your r will be simply the just like the lambda. Okay. So this is your y. The only or the problem here mostly is your dv. So how do you get dv? So to get dv, okay, that will be you'll have here pi, right? Because originally, okay, to show you that the formula for this method is v equal to the um, v is equal to integral of, I think it's still here. Here we go. R squared dh, right? R squared dh. R squared dh. But if since I need dv, so if I will take the integral of both sides, you'll have here dv is equal to, so the integral, if you take the derivative of an integral, they will just cancel out. So you'll be left here with r squared dh. Okay? And then so that will, what will happen here is dv is equal to, your r is still your y, right? So this is y squared, and your dh is dx. Okay? So So don't forget, I think I forgot the pi. Okay, so you still have a pi here and then so this will be your um, dv. Okay, so going back to il or the inertia, that will have 1 half m, which is your dv, and then your r squared is y squared. Okay, and then m dv. Okay, so you'll have here 1 half y squared, and your dv will be pi y squared. So you'll have something like, so if you will simplify this now, okay, you will simplify this now. So 1 half can bring that out, and then your pi we can also bring that out since we have a dx here, so we have to take the integral of that, and then that will be y squared y squared. So this is y raised to 4. So we have to get the value of y raised to 4 because this is in dx. So you have to make it in terms of x only. So we have the equation of the hyperbola is xy equal to 4, right? Therefore, your y here is just 4 over x. And then that will become 1 half pi integral of 4 over x raised to 4 dx. Okay. We still have the limit. So the limits will be just with respect to x, right? So the values of x is just between 1 to 4, right? So 1 to 4. So the limits must be, the lower limit is 4, the upper limit. And the lower limit is 1, the upper limit is 4. And then if you will use your calculator, you'll get an answer of 42 pi. And then this is your, get to the next number. For number 3, is to find the polar moment of inertia of the region bounded by r squared equal to a squared cosine theta. So this is actually a Leibniz case, but it is a special case of Leibniz case. So this is what it looks like. I already drew the graph of the equation. Okay? So what we'll be doing here, since we are asked to find the polar moment of inertia of this one, as you can see, they are just symmetrical in the four quadrants. Okay, so if you, I will say that this is 0, right, and then this is your pi over 2. So that's 90 degrees. So in radians, that is pi over 2. So what will I do is I will just be getting the inertia at the first quadrant. Okay, I'll be just getting the inertia of this one and then just multiply it by 4. Okay, to make things easy. Okay, so remember that the formula for polar moment of inertia, that is just 1/4 integral of r raised to 4 d. Okay, but you can also rewrite this as 1/4 integral of r squared squared d theta. Okay, so why did I do it like that? Because r squared, so I can just make it like this. So I can use directly the r squared equal to a squared cosine theta. Okay, so what will happen here is 1/4, okay, integral of, so r squared is a squared cosine theta, right? And then squared d theta. And then I have to multiply this, okay, multiply this by 4. Okay, I have to multiply this by 4 because this is due to symmetry. Due to symmetry. Okay. So how about the limits? So the limits will be just 0 to pi over 2. Okay. So you'll have here equal to 1/4, right? The one actually the 1/4 will be cancelled out with the 4 due to symmetry. Due to symmetry. So that will be a squared. So I can bring out the a squared, right? So that will be a raised to 4 because a squared, and then integral of cosine squared theta squared d theta, right? That's 0 to pi over 2. Okay, so if you will input that you're in calcu, you'll just get pi over 4. Okay, don't forget the a raised to. So this will be your polar moment of inertia. That will be your answer.